Welcome to this presentation. Now we are starting on equation number 6. Last time we ended on equation number 5. These are equations regarding the acid and base reaction. Question number 6 saying carbonated water is a solution of carbon dioxide in water. That means carbon dioxide which is mixed with water. This solution is acidic because carbon dioxide reacts with water to form carbonic acid. This is the formula for carbonic acid with 2 hydrogen and a carbonate. Then they're asking calculate the concentration of hydrogen, the bicarbonate and the carbonate ion. That means we need to calculate the concentration of hydrogen, the concentration of bicarbonate, and the concentration of carbonate ion in the solution with 0.033 molar of carbonic acid. So the concentration of acid was given. Again, the carbonic acid is diprotic acid. We have given a Ka1, which is equal to 4.3 times 10 power negative 7, and you have also the Ka2, which is equal to 5.6 times 10 power negative 11. This is what was given. The Ka1 and the Ka2 was also given. So now they are asking to calculate the concentration of H plus, the concentration of bicarbonate, and the concentration of carbonate. Let's see, this is the diprotic acid. It will dissociate. The first dissociation will give the H plus and the bicarbonate. This is the bicarbonate of hydrogen carbonate ion, and we have the Ka1. So then we have also the second dissociation where this one is going to dissociate. In the second dissociation, this is where we have this one, which is coming from the first dissociation, is going to dissociate to give the second hydrogen, then the carbonate ion. Now they are asking what is the concentration of these 2 hydrogen when they are added together. What is the concentration of the HCO3 minus the bicarbonate, and what is the concentration of carbonate ion. With this kind of question, we are going to use the IC table. Let's see from the first dissociation. First dissociation will be having this one, this one, and this one. Let's just develop a table. We'll be having the carbonic acid, which give the H plus this bicarbonate. Of course, before dissociation, initial state, we have 0.033 the carbonic acid. Here the hydrogen we don't have, and the bicarbonate we don't have. Then the change, we are removing the reactant, and then we are forming the product. That's why you can see negative X. Here we form plus X. Here also we form plus X. Then at equilibrium we have 0.033 minus X. Here we have X, and here we have X. Then we can just calculate the equilibrium constant, which is Ka1 will be equal to X times X, which is equal to X squared over the reactant, which is equal to 0.033 minus X. So we can assume that this X is negligible as compared to 0.033. If we assume X negligible as compared to this value, in this case we will be negating this X, and then we have Ka1 is equal to X squared over 0.033. Of course, when we are using this assumption, so you need to verify whether assumption is valid or not by calculating the percentage dissociation. So in this case, you can calculate the X. If we take this one and we try with this one, you get X squared, then X is equal to square root of Ka1 times 0.033. Then we get X is equal to 1.19 times 10 power negative 4 molar. Then after getting X, you calculate the percentage dissociation. We take the one dissociated because X is the hydrogen dissociated from the first dissociation. Then we take the one dissociated dividing with the initial one times 100. Then we get 0.36% as the percentage dissociation. So here assumption is valid because the percentage dissociation is less than 5%. That means the X or the hydrogen dissociated from the first dissociation will be equal to 1.19 times 10 power negative 4 molar. Again, also this the HCO3 negative after the first dissociation will be equal to 1.19 times 10 power negative 4. Then here the carbonic acid, which is remain and dissociate, will be equal to 0.033 minus X. That means the carbonic acid which will remain and dissociated. So H plus from the first dissociation, so is equal to X, which is equal to 1.19 times 10 power negative 4. Then you have the X is equal to the bicarbonate also. This is only bicarbonate from the first dissociation, because if it is going to do the second dissociation and this concentration will change, then the bicarbonic acid, which is the undissociated, this will not change. The only value which will not change in the second dissociation is this one. That means here we remain with the bicarbonic acid is equal to 0.0328 molar. That will remain at equilibrium because it will not participate in the second dissociation. In the second dissociation, this one will dissociated, and then after dissociation, it will contribute to more hydrogen in the solution. That means this one and also the hydrogen will change in the second dissociation. What you have is that we have this one, and you have the H plus, and you have the carbonate. But remember, after the first dissociation, we have this value for the bicarbonate. You have 1.19 times 10 power negative 4, which is concentration, and also we have this hydrogen. That means the second dissociation will have a common ion effect because we have already the hydrogen in the solution from the first dissociation. That means that this X, the hydrogen coming from the second dissociation, will be negligible because there is already some hydrogen from the first dissociation. That means here we have the common ion effect in terms of hydrogen. So let's see the X which will be dissociated from the second dissociation. So we have the X here, which is here, then 1.1 times 10 power negative 4 plus X. This is the term dividing with the reactant. So the Ka2 is equal to this one. If you assume X negligible, we assume this one negligible and this one negligible, then you get Ka2 is equal to this one and this one. That means X will be equal to Ka2. So X will be equal to Ka2 is equal to 5.6 times 10 power negative 11 molar. So the percentage dissociation, because we need to verify the assumption, you get this one. That means the assumption is valid because the percentage dissociation is less than 5%. So then, after the second dissociation, we will be having X, which is equal to the value that we have, 5.6 times 10 power negative 11 molar. So that is X. That is equal to also to carbonate ion. Then H plus will be equal to this one from the first dissociation plus this one in the second dissociation. That will be the total hydrogen in the solution, and that will govern also the pH of the solution. Then the bicarbonate will be equal to this one minus X. That means this one minus the X, which is this one. Then you have the bicarbonate, which is equal to this one negative X, this one minus X. That then you get 1.19 times 10 power negative 4. You can see adding or removing this one, the dissociated from the second dissociation, it will be negligible. So you can see either adding or removing it does not change the values. That means then at the end you have here the all species that we have the hydrogen, which is equal to this one, you have the carbonate, which is equal to this one, and you have also the bicarbonate, which is equal to this one, and you have also the H plus equal to this one. We can also determine even the hydroxide, and you have also 0.03288 molar of bicarbonic acid, which remain undissociated at equilibrium. And this one we have seen it in the first dissociation, that will not change. So these are the values that we'll be having for this question. Let's go to question 7. Question 7 is saying concentration of H2S in a saturated aqueous solution at room temperature is approximately 0.1 molar. Then calculate the H3, the H plus, the hydroxide, the HS minus, and the S2 minus in the solution. So it's the same. We also, because we have the diprotic acid, we have to dissociation. Let's first go, we have given also the Ka1 and the Ka2. It was given in the question. Let's first go to the answer. Today we are trying to move very fast because we have covered the first section and we have seen how we solved it. So we have the first dissociation and also the table for the first dissociation. That means we have 0.1 molar of H2S. Initially, we don't have the product, we have only H2S as reactant. Then the change, we have the reactant which are going to be removed and the product are getting formed. Then you have also the equilibrium. Then we can determine the X. If you assume X negligible, then we can have the X is equal to this one, this value 9.43 times 10 power negative 5 molar. Then we check the assumption, whether the assumption is valid by calculating the percentage dissociation. Here we can see that the percentage dissociation is less than 5%. That means assumption is valid. Then you can say that X is equal to this value 9.43 times 10 power negative 5 molar. Here it is a percentage and not the molarity. Then we have also here, this is the H plus from the first dissociation. Then we can determine the HS minus is equal also to H plus because they are X and the X. We have also H2S which is equal to 0.1 minus X, which is equal to 0.1 minus this value which is X. We get 0.1 molar. So the other values, they are going to change because this one HS minus will undergo the second dissociation, and also this one will also change because we need to add the hydrogen from the second dissociation, and this one is the one which will remain undissociated and it will remain at equilibrium. That means we have now one value which is H2S, which will be remaining at equilibrium, which is equal to 0.1. Now let's go to the second dissociation. The second dissociation, this one is going to dissociate by giving H plus and S2 minus, but remember also we are having H plus dissociated from the first dissociation. We have also HS, remember from the first dissociation, that is what you have. We have also this H plus from the first dissociation, and initially here we don't have, we have 0. Then that means this HS will be removed and it will be forming H plus and it will be forming S2 minus. This is what will happen at equilibrium. We add them. We take this one negative, this one plus this one, and this one plus 0 plus this one. So then we calculate the Ka2. Here we use Ka2 because we are in the second dissociation. So that means we replace this one, this terms here, plus times X. Here also we divide with this one, which is the reactant. Then we have assume that X is negligible. In this case, we have X is equal to, can cancel this one, that means X will be equal to Ka2. So the X will be equal to 1 times 10 power negative 19. If you calculate the percent dissociation, you can see that here the assumption is valid. Then you can say H plus from the second dissociation is equal to 10 power negative 19. Then S2 minus, of course, S2 minus is equal to X also, which will be equal to 10 power negative 19. Then H plus, the HS, you can take this one negative X. That means this one 9.43 times 10 power negative 5 minus X. Then you get this one, and for the H plus, we take this one plus X. X is equal to 10 power negative 19. Then you get this one, and also we have the one H2S which you get from the first dissociation, which is not changing. Of course, you can also determine the hydroxide if you want by taking 10 power negative 14 dividing with the concentration of H plus. So that is how the hydroxide can be determined, by taking 10 power negative 14 dividing with the concentration of H plus, which is equal to this one. Then you get 1.06 times 10 power negative 10 as the concentration of hydroxide at equilibrium. That was question number 7. Let's move to question number 8. Question number 8, it has a different sub-question. It has a question, sub-question A, sub-question B, and a sub-question C, if I do remember. Let's quickly start on sub-question A. It is saying salicylic acid and its derivatives have been used as a pain relief for a long time. A salicylic acid occurs in small amounts in leaves, bark, and roots of some vegetation, most notably historically in the bark of the willow tree. Extract of these plants have been used as medication for centuries. So they have been using the extract as a medication purpose for centuries. The acid was first isolated in the laboratory in this year. So all this information, they are just to give it to describe what is a salicylic acid and its derivatives. So we don't care about all this starting information. They are saying both functional groups of salicylic acid ionize in water with Ka, which is equal to 1 times 10 power negative 3 of carboxylic acid group, and also we have another group which is hydroxide, which has a Ka which is equal to 4.2 times 10 power negative 13. That means it is a diprotic acid because it's having two functional group which act as the acid. Like for example, this is one where the carboxylic acid group will dissociate, and also the second H plus from OH will also going to be dissociated, and all of them the Ka was given. Then they are saying what the pH of saturated solution of the acid solubility is equal to 1.8 gram per liter. So that means the acid will be determined by the hydrogen dissociated from this one plus the hydrogen dissociated from this one. But we need to check which one is going to dissociate on the first by looking on the Ka. Like for example, this Ka for carboxylic acid is 10 power negative 3, and for hydroxide is 10 power negative 13. That means the carboxylic acid which has a high Ka value is the one which is going to dissociate the first to give the first hydrogen in the solution. Then they are saying what is the pH of saturated solution. Here we need to know what is the definition of saturation. That means is the solution which has the maximum solubility. That means the maximum solubility of this salicylic acid is 1.8 gram per liter. Here we can determine then the concentration of salicylic acid from the solubility. Of course, we need to change this one, the grams, into mole. Then we get the concentration of salicylic acid. Let's see as the answer. So that means we need to determine the moles. So we have the molar mass of this salicylic acid, which get 138 gram per mole. We have also the solubility that was given as 1.8 gram. That means 1.8 gram of solid per liter of solution. Then we can convert the gram into moles. After converting gram into moles, we are taking gram dividing with the molar mass so that we get gram moles. Then we have 0.013 mole per liter or molar as the concentration of salicylic acid. Then salicylic acid is going to dissociate. That means the first carboxylic acid group is the one which is going to dissociate first. The compound has two dissociation constant. The first dissociation will be the one with high Ka value. This is for the carboxylic group. The second dissociation, that means the hydroxide group will dissociate on the second, and it is also a common ion effect because there will be hydrogen dissociated from the first dissociation. So let's see, continue as the answer. We have the first dissociation, which will give this one and this one. So here we have the concentration which was given. We can have calculated from the solubility. Then you can say the Ka, this is the Ka from carboxylic acid that was given from carboxylic acid group or COOH group. So we have this table. This one is this one, which is say to give this one. This one initially you have 0.013 of this salicylic acid. Then we don't have this one, we don't have this one. As they change, this will dissociate, forming this one and this one. Then you have the equilibrium, which will be equal to this one. We can calculate the dissociation constant Ka, which will be equal to x times x, which is equal to x squared dividing with the reactant, which is equal to 0.013 negative x. Then we replace the Ka, which is 10 power negative 3. Then we have this one, and we have this one. You can assume that this x negligible. If we assume x negligible, then we get x is equal to 0.00361 molar. Then we check the percentage dissociation. You see that we have 27.74%. That means our assumption is not valid. We cannot get this x. Now we are going to move to the quadratic equation. Then we are going to solve the quadratic equation so that we get the hydrogen dissociated from this first dissociation of salicylic acid, or the dissociated hydrogen from carboxylic acid, the group of this acid. So we have here, then we don't ignore x, and we see how the quadratic equation is obtained. Yeah, we do different rearrangement, and then we obtain the quadratic equation. After getting quadratic equation, we look for determinant. You know, determinant is equal to b square. This one is square minus 4b minus 4a times c. So this is c, this is a, this is b. That when I'm talking b square, I'm talking this term square. Minus 4, this is the a is 1, and then c square. So this is you have covered this one, how to solve the quadratic equation. Then after getting the determinant, we calculate the square root of the determinant. Then we solve for x1. This will be rejected because the concentration cannot be equal to negative. Then we also see x2. This is not x1. This is the X2, not this X1, and this is X2. Then you get 0.00314 molar. That means the dissociation, the hydrogen which will be dissociated from the first dissociation will be equal to 0.00314 molar, and that will be the hydrogen dissociated from the COOH of the carboxylic acid group. So after the first dissociation, then you have the X, which is equal to this one, X is equal to H plus is equal to this one. Then we can have the remaining, and dissociated acid will be equal to 0.013 minus X. Then you get this one. So the second dissociation will involve the liberation of H plus from the hydroxide from the OH group. Then keeping in mind that we have also the hydrogen dissociated in the first step. So then we will be having this one dissociating, liberating also the H plus from the hydroxide. Then we have this one, you have the Ka. But remember, we have the concentrated H plus dissociated in the first term, which is equal to 0.00314. And also we have this one, its concentration is equal to 0.00314. And its concentration, we get them from the previous dissociation, from the first dissociation. The remaining others, the IC table, we are removing this one, forming this one and this one. We have also the Ka, but this Ka, we are using the Ka for hydroxide group, which is this one. Then you can make this one negligible. If you make this one negligible, then you will get here, this one is equal to X, because this one will be cancelled. The X will be equal to 4.2 times 10 power negative 13. Then we check whether the percentage dissociation is less than 5%. Yes, you can see that the percent dissociation is 1.34 times 10 power negative 8, so which is less than 5%. Here, assumption is valid. That means we have the X dissociated from the second dissociation, or X dissociated from the hydroxide of the acid, will be equal to this value. This value, 4.2 times 10 power negative. This value, 4.2 times 10 power negative 13. 4.2 times 10 power negative 13. Then H plus, we take this one plus this one. That means this one, this one plus X plus this one plus this one. Then here that will be X, it will be equal to this one. Then here we take this one minus X. That means this one minus the X. Then that's what we'll be having. So here, that's what you have after the second dissociation. You have this one, the one remained undissociated in the first dissociation. We have this one, which will be equal to this one minus X, because X we obtain, that is 4.2 times 10 power negative 13. We get this one. We have also this one, which is equal to X, and also we have H plus, which we need to add the one from the first dissociation plus the X from the second dissociation. We get this one. Then to calculate the pH, we take the total hydrogen. That means the pH will be equal to negative log of H plus, but it is the total hydrogen which is equal to negative log of H plus, negative log of 0.00315. You get a pH of 2.5. So let's go to question 8b. Question 8b, what is it asking? It is saying aspirin was discovered as the result of effort to produce derivative of salicylic acid. So we have seen the formula for salicylic acid in 8a. Now they are saying that they have produced aspirin from salicylic acid. So this was because we were producing a derivative of salicylic acid that was not irritating the stomach lining. So to avoid the irritation of the stomach, they have changed. They have then look. They have developed the derivative of aspirin, which is they have derived the derivative of salicylic acid, which is aspirin. Then from salicylic acid, they have produced the aspirin. Aspirin is the acetylsalicylic acid. That means they have taken the hydroxide group and they have added the acetic acid to the salicylic acid. You can see the hydroxide group was replaced by the acetic acid. This is acetic acid group. The function group here that will be having, we are remaining only with the one function group, which is the COOH group. That is only one function group. So, but it is still present, but they are saying it has reduced. The Ka is 3.3 times 10 power negative 4. It is no longer 10 power negative 3 as it was before. It has reduced. The acidity was reduced. Then they are saying what is the pH of the solution. of aspirin with the same concentration as the saturated solution of salicylic acid. That means here we are going to use the same concentration that you have used for salicylic acid. Now they are saying if the concentration is the same, if the concentration of salicylic acid is the same, then they are asking what will be the pH, but if the Ka has changed. So here, then we move very fast because we have only one function group, which is the CO. We have only one dissociation. So it's very simple here. We just use the IC table to see this one will dissociate to give this one and this one. This is the Ka. Let's see the table. So this is the table. They are saying the concentration the same as the salicylic acid. They remember the or 0.013. Then here initially you have 0 and here you have 0. Then we do the change. We remove the reactant by forming here the product. From here the product, and this is what will happen at equilibrium. Then you calculate the Ka. Assume X as a negligible. Then you get this is negligible. This means Ka will be equal to x squared over 0.013. The Ka was given, so that means 3 times 10 power negative 4. Yes, is it 3 times 10 power negative 4? Then we are going to look for x. So then x will be equal to 0.001975. But we need to verify whether assumption we made is valid. So here you can see that the percent dissociation is higher than 5%. Here the assumption is not valid. We need to determine the quadratic equation, and we need to solve the quadratic equation to find the x which is dissociated. So we just rearrange and get the quadratic equation. So that's the quadratic equation that we need to solve. Then we determine the determinant. After the determinant, we just determine the square root of determinant and determine for x1. Here, because it is negative, we rejected. There is no concentration which is negative. Here this is the x2 not x1. Just correct it's x2 not x1. Then you get 0.0018 formula. That means this is hydrogen dissociated from this acid. So here then you get the pH is equal to negative log of this concentration that you obtain. You get the pH 2.74. That was for question 8a. Let's go to question 8c. What is this asking? It is saying under some condition the aspirin. Remember we say that aspirin is coming from salicylic acid, which is going to be in which we have acetylated. We have added the acetic acid group by removing the hydroxide. Here then the aspirin is going to be split to the back. Aspirin react with water and form a solution of salicylic acid and acetic acid. So assuming that we have aspirin and you have split into two by reacting with water. So that's what, if react with water, it will give back the acetic acid and the salicylic acid. They are saying write down the reaction of hydrolysis of salicylic acid, which write down the reaction of hydrolysis of salicylic acid. That means here we are going to indicate how this hydrolysis is performed. Which of the acid, salicylic acid or acetic acid, they produce more hydronium ion in such solution? Then they are saying if you have, for example, salicylic acid and acetic acid in the same medium, which one will produce more hydronium ion? Of course, the one will produce more hydronium ion is the one which has the high Ka value, a function group. Then they are saying what are the concentration molecule in the ion solution produced by the hydrolysis of 0.5 gram of aspirin dissolved in enough water to give 75 ml of solution. The K of acetic acid was given. Here they are saying write down the reaction of hydrolysis of salicylic acid. I think here it is not salicylic acid. It is the hydrolysis of aspirin rather than salicylic acid. So let's see here. We just get the answer. So for question 8c, the first one, during hydrolysis, water breaks one or more chemical bonds. This is what we have. We have here, we can split it here so that you can get the acetic acid plus salicylic acid. That's what we get if we do the hydrolysis, because they are asking to write down the hydrolysis reaction. So then they are asking which one will produce more hydrogen in the solution. Here it is obvious that the acetic acid, go to the Ka, the of acetic acid, it is going to have here, we have the acetic acid and you have the salicylic acid. Salicylic acid, they have it's a Ka of the function group, which is the carboxylic acid, which equal to 10 power negative 3, I think. Yes. Then they are saying by comparing the Ka, you can get 10 power negative 3. That is the Ka for the function group of salicylic acid, which is the carboxylic acid, the group of salicylic acid, is having the Ka, which is equal to 10 power negative 3. And for acetic acid, we have the Ka, which is equal to 1.8 times 10 power negative 5 as a carboxylic acid group. You can see that here, this one, which is a salicylic acid, is the one which is more acidic, is the one which will contribute more proton as compared to the acetic acid. Then the hydroxide group, of course, it will contribute less because if you remember, it is having around 10 power negative 13 as the dissociation constant. This will be the last to dissociate. Now we need to determine the ions or the ion in the solution. That's what we need to determine what will be the ion and the molecule at the equilibrium. That means we need to dissociate the acetic acid, we need to dissociate the salicylic acid, and also we need to dissociate the hydroxide group from salicylic acid. That means the first dissociation will be from the salicylic acid, carboxylic acid group. The second dissociation will be the acetic acid. Then the third one will be dissociation of hydroxide from the salicylic acid. Let's proceed. Let's proceed. This is what we have. This one, the first dissociation will be dissociation of this one. There will be hydrolysis first. We have acetic acid plus salicylic acid. This is the mixture that we have. And this one will be the first to dissociate because it has the carboxylic acid group, which has a high Ka value. The second dissociation will be this one, acetic acid. Then the third one will be the hydrogen from the hydroxide. Now, what is the concentration that was given for aspirin? So, aspirin, the concentration they have given the mass, which is 0.5 gram. Then you divide with the molar mass to get the concentration. Then, after getting the concentration, you can see that here 1 mole of the aspirin react to give 1 mole of acetic acid and 1 mole of salicylic acid. That means the concentration of acetic acid and the salicylic acid will be equal to the concentration of aspirin. So now we can then do the table, the IC table, to see which one is going to dissociate. This one, I told you that the carboxylic acid, the group from salicylic acid, will be the one to provide the hydrogen in water for fast dissociation. Secondly, the acetic acid will be the second one to dissociate. Then lastly, the hydroxide will be the last one to dissociate. So this is what will happen from the first dissociation. We are going to lose the hydrogen from the carboxylic acid group of salicylic acid, which will be liberated to the solution. Then this is what will happen. We have 0 here and 0 here, and we form X and we form X. Here we do minus X. This will be at equilibrium. Then at equilibrium we have this one. If we assume X negligible, that is what we get. We get X equal to 0.006. We verify the assumption. You see that here we cannot use the quadratic equation. Let's quickly solve the quadratic equation. This is the quadratic equation. We determine the determinant, we determine the square root of the determinant, we determine the x1, which will be rejected because the concentration cannot be negative. Here we develop x2, here is x2 not x1, then you get 0.0056 more. That means the H plus dissociated from the carboxylic acid of salicylic acid, there will be this one. Then after the first dissociation, you get the H plus, the one dissociated from the salicylic acid, we get also this one, and we will be equal to 0.0056 more. That means this one and this one will be undergoing the second dissociation because this one will be dissociated. Then we will have the hydrogen which will add. But this one is not the one undergoing the second dissociation because we have the acetic acid inside. That means this one will dissociate on the third step. Second step, that means the acetic acid is the one which is going to dissociate in the solution. But remember that we have also the H plus coming from the first dissociation. This acetic acid will have a common ion effect in terms of hydrogen. So that's what you have. We remain if we dissociate the acid. After the first dissociation, we remain for 0.037 minus X. That means we have 0.031 formula. That means this is what will remain and dissociated, and it will be in equilibrium. Then this one that we have determine here, it will go in the third dissociation, because the second dissociation will be the acetic acid dissociation. Let's see how acetic acid is going to dissociate by giving, but remember here, what you need to remember is to make sure that you know that there is the hydrogen coming from the first dissociation. Don't ignore it, please. Don't ignore the hydrogen coming from the first dissociation. Then we determine the X, assume the X negligible, and we calculating the X. You see here the percent dissociation is varied. So here the X coming from the acetic acid will be equal to 0.000119 molar. Here assumption is varied. That means the X coming from the acetic acid dissociation, it's also is equal to this one, the acetate ion. Then we will be having this one. Then after the first and second dissociation, you have the acetate ion. So we have also the H plus, because we need to put H plus from the first dissociation from salicylic acid plus H plus from the acetic acid dissociation. Then we have this value after the second dissociation. Then we have also the acetic acid which will remain undissociated. We take this one minus X. So we get this one. This will be undissociated acetic acid. We have also undissociated the salicylic acid that we get from the first dissociation. Then we have also this one, which is also 0.0056 molar, which is going to undergo the third dissociation, because there is the hydroxide here, which the OH is going to be also liberated to the solution in the third step. So now this one, the third dissociation will involve the OH, but we'll be having the H plus dissociated from the first, from salicylic acid, and the H plus dissociated from the acetic acid. Don't forget also that information. So we have this 0.0056. So this is the concentration that we have in the first dissociation. We have also 0, and here we will be having here the 0.005719 as the total hydrogen, the hydrogen coming from salicylic acid dissociation, carboxylic acid, on carboxylic acid group, and also the hydrogen dissociated from the acetic acid. This is the total from the first and second dissociation. Then here is the same as we did. So we determine the X. So we make the assumption and see whether the assumption is valid. So you can get the percent assumption. You can see here the assumption is valid. Then the X from the hydroxide dissociation will be equal to 4.11 times 10 power negative 13. Of course, it is very small. It can be negligible if you add them. Then at equilibrium, total H plus will be this one plus this one. This one will be X, and this one will be this one negative this one. So that is what we'll be having. We'll be having X, which is equal to this one. X is equal to this ion. We'll be having H plus, which is equal to total H plus. We'll be having also this one, which is equal to 0.0056. The concentration molecular ion that will be present, then we have undissociated this one. Remember, we get it from the first dissociation. We'll be having also 0.056. This is one. So we'll be having this one. We'll be having undissociated the acetic acid. So you get to remember this one from the second dissociation. Then we'll also be having the acetic acid, the acetate ion, which is equal to this one. And at the end, we'll be having the total H plus from the first dissociation of carboxylic acid, of salicylic acid. We'll also have the H plus from the acetic acid, and also H plus from hydroxide. Then you get the total H plus, which is equal to this one. We can also include the hydroxide, which will be equal to 10 power negative 14 dividing with the H plus, and then you get 7.75 times 10 power negative 12 more. Hope that this was clear. It was a long question. So let's go to question 9. Question 9 is saying the ion HTE is an apoprotic species. It can be act as either an acid or a base. Of course, if an ion is coming from the weak acid, it can act as an acid or a base. Then they're asking write down the expression of Ka for H2TE acting as an acid in water. Then they are saying write down the expression of Kb for the reaction in which HTE function as a base in water. then show that the product of Ka and Kb equals to Kw. Then they are saying what is the value of Kb1 if the Ka1 for the H2T is equal to 2.3 times 10 power negative 3. So it has also another sub-question which say write down the Ka expression for the acid reaction of HTE with water. Write down the Kb expression for the reaction of Te function as a base in water. What is the value of Kb2 if the Ka2 for the H2E is 1.6 times 10 power negative 11? So we have also another sub-question for this question. It is saying demonstrate whether or not the second ionization of H2Te can be neglected in the calculation of HTE in a 0.1 molar solution of H2Te. What is the concentration of this acid? They are asking the various concentration H2Te, HTE, Te2 minus, and H plus in a solution if this 0.1 molar solution of H2Te is present. So for this kind of question, what you need to know is that for each acid, it has a conjugate base, and then we can calculate the Ka from the acid and the Kb from the base. If you take Ka times Kb, you should get the Kw. Let's see, for example, this question number I, how to solve it. It is saying the ion HTE is a pyrotic species. They are saying write down the expression of Ka for H2Te acting as an acid in water. That means to act as an acid in water, it will liberate the hydrogen, because the acid liberates the hydrogen in water. That's how it will act as the acid. Then they say they write down the expression for Kb for the reaction in which H function as a base. That means if it is functioning as a base, it will attract the hydrogen, liberating the hydroxide. Then they are asking show that the product of Ka and Kb equal to Kw. Then they are saying what is the value of Kb1 if Ka1 for the H2Te is 2.3 times 10 power negative 3. Let's see for this question number I, the first situation we have this one. This is the acid. This is the conjugate base. That means this will behave as an acid and this will behave as a base. Behaving as an acid, that means it will liberate the H plus in the solution. The H plus from here will react with the water to give the hydronium ion. So this is, we have the Ka1 because it is acting as an acid. Then what will be Kb? With Kb, this one this will be Ka, this will be Kb. That means if this Kb, this one will react with water by attracting the hydrogen from water, giving this one and this one. Then we have the Kb1. Then this Ka1 times Kb1 should be equal to Kw. Let's see. So Ka1 times Kb1 is equal to this one. This is this terms times this term. Then you get Kw, because if you check, this one will be cancelled with this one will be cancelled with this one. Then that means Ka1 times Kb will be equal to this one times this one, which is equal to Kw. So we have shown that. Then they are saying if now we have the Ka, which is equal to 2.3 times 10 power negative 3, then what will be the Kb? That means the Kb1 will be equal 10 power negative 14 dividing with Ka1. Once you have the Ka or Kb, you can determine the unknown. If you have Kb, you can determine Ka1. If you have Ka1, you can determine Kb1, because you know their product is equal to Kw. That was question I. Let's go to question II. It's also the same. It involves the second dissociation. That means HTE will behave as an acid by liberating the H plus in the water. Then this one will be act as a base by attracting the hydrogen. So that means the acid reaction constant HT will be the Ka2 for H2Te. That means because it is coming from the second dissociation. Then Te, it will act as a base. This one, then you can take Ka2 times Kb2, then you will be getting that it is equal to Kw. Again, if now the Ka was given, then you can calculate the Kb2. K was given as 1.6 times 10 power negative 11, then you can calculate the Kb2, which is equal to 10 power negative 14, dividing with the Ka2. So you can see that here also is just the writing the equation and showing that the Ka is equal times Kb is equal to Kw. The next question, they were saying that we have this Ka1, and they were saying that we need to show that the second dissociation can be negligible. So let's see, we have this acid which is going to be dissociated from the first dissociation. We have 0.1 molar. This is what we be having 0, and here we have this at equilibrium. Now we need to show that the second is negligible. Here we can have the for x from the first dissociation. Let's see here, percent dissociation is this one. We cannot, the assumption is not valid. We proceed for the solution of the quadratic equations. Here we get the quadratic equation and then you solve it. After solving it, we see that the x2 will be equal to 0.01385 molar. That means here this is the dissociation from the first dissociation of this acid. So this is the hydrogen dissociated from the first dissociation will be equal to this one. So that means we can go this one and this one, they will be equal. That means this one will go to the second dissociation, but also we have H plus from the first dissociation. So there will be a common ion effect. So then we have the second dissociation, which will consider also the common ion effect, because we'll be having the H plus, which is coming from the first dissociation. Then after, then we need to calculate the X. We have the X is equal to Ka2, which is equal to this one. For us to know that it will be negligible, if we take X and we add it to this one, and we don't see the change, that means it will be negligible. Here also, if you take this one minus this one and we don't see the change, that means it will be negligible. So we can calculate the percent dissociation. Here the percent dissociation is less than 5%. That means here we will be having the assumption which is valid. So we have the X, then let's see if you take this concentration plus this X, you can see nothing is changing. So here also you take this concentration minus X, here also nothing is changing. So we can say that the second ionization can be negligible, because it is very small as compared to this value. Then the species, they were all asking what are the species at equilibrium. We have determined them. This one, this is T, the X, we have it, the H plus, we have it, and also the HT, we have it. The H2T, we have it at equilibrium. So these are the concentration at equilibrium. Let's go to question 10. So then we end on this question today. Which of the following concentration and in which condition would be practically equal in calculation of the equilibrium concentration in 0.134 molar solution of this H2CO3? They are asking if what are these that will be equal and in which condition, and no calculation needed to answer this question. They are saying, is this one equal to this one? Can this one equal to this one? Let's see now if you have if you go to the answer, we see that we have the first dissociation here. We have also the second dissociation. If we try to develop a table here, they are asking in which condition one of these conditions, is it this one is equal to this one, or this one can be equal to this one? That's what they want to know. Which ion will be equal, and in which condition do we have equal concentration of this ion? So that means this is what you have, the X1 and the X1 at equilibrium behaving this one after the first dissociation. If you move to second dissociation, that means X1 is the one which is moving to the second dissociation. This one, X1 moved to the second dissociation. We have also X1, which is H plus from the first dissociation. Then here we have 0. That means here we have the bicarbonate acid, which will be equal to this, the bicarbonate ion, which is equal to X1 minus X2. H plus will be equal to X1 plus X2, and then we will be having here X2, which is equal to carbonate. So the only possibility, the only ion which can be equal is this one. This one can be equal to this one. The H plus can be equal to the bicarbonate ion. In which way? This is when this X2 is negligible. When this one is negligible and this one is negligible, in this case here the H plus is equal to X1 and this one also equal to X1. then the only condition is when X2 is negligible. When the second dissociation is negligible, when the second this amount of the dissociated hydrogen is negligible. In this case, we have the H plus equal to HCO3 minus. Because they were asking in which condition. The only ion which can be equal is the H plus and here and the bicarbonate, and the condition is that the X from the second dissociation X2 should be negligible.